too good with me. But thank you, and also thank you to all the organizer and the committee for inviting me and giving me the opportunity to share with you, let's say, our perspective. So it is based on complexity science, about computational social science, and overall the role that our techniques and our models can have to trace human behavior online, and how we can safely and positively use this information to say something good and to learn something about collective behavior online. So I share the screen, and I want also to thank all the students who made it to survive until today. I have seen the schedule is pretty tough, so thank you very much for being here also for me. So I want to start with with this video, just telling you also some numbers about our usage of internet and social media today. So almost 5 billion people nowadays spend more than 5 hours per day on the internet doing something. And as you can see, many of them use the internet when they should not, actually. And collectively, in 2019, we have spent more than 1 billion years online. That is amazing if you think in terms of numbers. So when I say collective, it means by summing up all of our times spent online. And 40% of the time is spent on social media. So let me say that this is a pretty relevant and pretty important, because social media are nowadays part of our lives in one way or another. It can be, or you can think that it's good or it's not good, but it's what it is. So we have to deal with it. And as you can see from the numbers, the trends are really astonishing. So there is an increase in the human population, of course, but there is also an important increase, a stable increase of 7–10% in the number of users of internet, and also 9–10% in the number of users of social media, and in the number of users of mobile phones, even if the rate is a bit slower. But with 5 billion users, unique mobile phone users, you understand that it's really relevant to study computational social science in this period. So it's exciting, and it must be exciting for all of you to study this in this period, because it can have really impact, and you can learn a lot about our society. So this is from a work in progress, and it's just statistics collected from a data set that has been shared with me from the CEO of About.me. And it's just to show that this is the number of the percentage or the fraction of users and present with at least one account or more accounts in a certain number of platforms. And you can see that, yeah, there is a peak around 3 platforms of social media, but there is a long tail about that. So with people having up to 20 active accounts on 20 distinct virtual platforms. So this is amazing to me, because it requires a lot of attention to spend online. And once you see that those platforms have also some correlation. So the probability that if you have a Twitter account, you are also on Facebook is large, just to give you some examples. And so as Michele told you, I am a network scientist. And network science is relevant. Most of all, we have discovered in the last 2 decades why it's relevant. For many reasons, but when it matters when it deals with the society, it's important, because if you put something to spread in a social system, it will do, and it will do very, very efficiently. It can be a deadly virus spreading through the mobility network, as you can see here, for instance, this mobility network in New York, or it can be a piece of information, a rumor, spreading on Twitter, for instance. So this is, again, real data. So what we are going to discuss today, mainly there are two parts in this in this lecture. In the first part, I will try to convince you that networks matter in general and complex networks. So we will discuss about some topological effects and emergent phenomena with specific case studies. And I will very quickly introduce you to the, let's say, the basic, the foundation of multi-layer network analysis, because it's relevant to better understand the second part, where will we explore the behavioral digital traces during COVID-19. Particularly, I will describe the work done by my lab in this field, especially about the infodemic. Maybe you have listened to it around, and I will discuss about entangled phenomena on networks, in this case infodemic and epidemics, together as well with other very recent results. And I also will spend some time to discuss the limitations of this type of approach, because a lot of people tend to forget that there are also limitations when we use these tools. So the fact that I am convinced that everything is connected to everything else, but I like to share with you that this vision is not new, and so it's not of the human of the human society, but it goes back even to Galileo, where during his studies he tried to connect different parts of different disciplines and trying to understand what is connecting to what else across the disciplines. And this is eventually the real spirit of network science, the fact of finding applications across disciplines. That's why it's a highly interdisciplinary field. And it works pretty well at different scales of space. For instance, here I show a network, describing synapses, and so let's say a model for the brain that is at a very small scale, but with billions, 100 billions neurons and synapses. And here instead I show a snapshot of a model of the cosmic web, where we have more or less even so the same number of galaxies, the neurons, but many more connections along the filaments. And the volume, of course, is at totally another scale. There are 83 order of magnitudes of differences between these two scales. But we don't have to go to the universe to find a network, other geometric networks. Here I show, for instance, cities. So the organization of cities here in the top panels over there. And here instead, there is the geometric organization of neural networks. So these are real neural networks, real neural cells. And these are real cities. And you see that geometric pattern, the spread of links across the space, has pretty similar patterns that are interesting to study. And another important feature of networks and of complex adaptive systems in general is that they share information, and the information flowing between the units of a network make the network responsive to what is going on in the outside, but also to what is going on in the inside of the network. And I love to share these fantastic examples of flocking birds. Probably you have seen this sometimes, but also the schooling of fishes and the swarming of insects. All of these processes are based on rapidly changing networks, and where the units can be insects or birds or fishes exchange information for some reason. Maybe they want to confuse predators, maybe they want to build some kind of shield for the collectivity, but it's essentially a very nice example to think about in nature. And there are other universal mechanisms that are exhibited by complex systems, and especially by networks, across a wide range of scales, as I was mentioning before. So here, if you want to play with these animations, so you can do it by yourself following this website. And let's move to one important process. I will tell more about the effects of this later, but why this is so I think that this is very important to understand. So it's about information cascade. I don't want to say anything about the underlying network. So here we have a complex network. It can be or a social system if you want. And here, just in this representation at the center, there is someone willing to share something. It can be a virus or it can be a piece of information. And once you see that there are some neighbors around this guy, the central guy, labeled here as 0, and not all of them will take activated or infected, if you want, in the same way. There will be some of them that will be infected, and some of them that will not. And at the second step of time, the same process happens, and you have a second order neighborhood of where there will be the activation of of this process, and so on for next times. This is in general more complicated, of course, because the network is not as simple as a tree. This is a real network. This is Twitter. During the final of a popular program, if I remember correctly, this is X Factor. And here each point is a user, a real user on Twitter. And the connection over there are replies and retweets between the user. You see that at some point there is someone tweeting something interesting, and there will be the cascade, they will be initiating the cascade that will spread across the network. But there are some many other examples that are now a decade old. For instance, the study of diffusion network related to politics, or in this case, US politics, but also in other countries, for instance, in Egypt, Japan, and Syria. You see that the structure here is somehow different at the eye, at the human inspection by eye. But once you analyze those networks, you see that there are really universal features that are repeated and that you can find across all different instances of these processes. And so what I want you to remind is that on the one hand, the information cascade is a good paradigm for spreading phenomena, but be aware that it's not the paradigm. So you cannot use always the same process for modeling any type of spreading phenomenon. For instance, a virus does not spread exactly like a meme on a social network, as well as a behavior does not spread exactly like a virus. There are things that intervening factors that depends on the units on the system that you are analyzing, like from non-locality, from the non-conservation of quantities like the mass, broadly speaking, threshold, complex contagion. So it's this is a paradigm, okay, but it's not how all the world works, and it's pretty important to remind. And then why network matter? Because depending on the structure, you can identify substructures. This is a typical example where you have a network of retweets again on Twitter, and here you have the English speaking users talking about USA, and here you have the Arabic speaking users talking about USA. And you see that there are two different communities, two groups that are very, very tightly linked by just one link. This is important for information spreading. And the same happens here, where you have, for instance, the subsystems related to the BBC News, for instance, and the other one related to the Fox News, which is a different broadcasting company. And many factors are relevant when analyzing this type of systems. For instance, the way the units, so the individuals, are connected together can be such that they can trap the information flowing inside, as here. In this way, you will have, for instance, a roadmap towards the emergence of echo chambers. But then you have also other other possibilities. If you have a high clustering, so it means that the individuals tend to create a triad. So the friend of my friend is also my friend, if you want. There will be the possibility of multiple exposure to the same piece of information, thus acting as a social reinforcement process. Thing that does not happen pretty well when you have low clustering. And then you can have homophily. This is a typical example. The speakers using the same language will tend to connect together, for instance. So there are many things important. But why I want to mention this? Because, for instance, when you think about nowadays, so you are familiar with the concept of influencer. So an influencer is a guy like this, where you have essentially a big guy with a lot of followers trying to spread some kind of information, like advertising a product or whatever. And what happens in this type of systems is pretty easy to forecast. It happens this. Essentially, the guy will get more attention, a bit more attention. There will be a larger number of followers, probably at some point, but you see that the followers are not really engaged or spreading that news. This is real data. Instead, if you have another type of structure that is more connected, more shared, less centralized, let's say, so more decentralized if you want, the result will be this one. And this is pretty relevant because in this network, people is more engaged about the piece of information circulating in that moment with respect to this one. So this type of network is more relevant than this type of structure, if you want, in advertising a product. And let me show also another example from real data. This is from one of my first papers in this field. This is the spreading of tweets about the discovery of the Higgs boson. Higgs boson was the discovery of the century because it was called the God particle and so on. It was very important for theoretical physics. I am a physicist by training, so I realized at the time the importance of this discovery. And here I show the distribution of the activity before, during, and after the announcement of the discovery, and the corresponding network, geographic network of interactions between between users. And this is a very important factor that you cannot, for instance, analyze a system when it finished. Or just aggregating all of the temporal information that you have and just analyze a static network. Why? Because there are different dynamics in space, as you can see here in these columns. So the tweets, the number of tweets, and the distribution of tweets during and after and before the main announcement are just different. In one case, you have a type of distribution. In another case, you have other distributions. I don't want to go into the details, but in the case of intertimes, for instance, so the times between two distinct tweets sent to the system, you have before and after a kind of power law scaling with tau to -1, and during instead the main event, you have a log normal. This is pretty important because the mechanistic models used to explain these two distributions are pretty different. So the message here is just don't aggregate in time if you have temporal data. But then in another paper that I have done some years ago with Elisa Modei, so one of my colleagues talking in this school, we have discovered that the same applies also when you consider different type of interaction. So if you disentangle the actions that you can perform on Twitter, in this case, for instance, in terms of retweets or engagement, direct engagement, mentions, and replies. Sorry, this is the retweets is direct endorsement, and while replies are more about engagement. And you will see that the distribution of the number of these interactions will follow some law. We have made the analysis. These are typical scaling, scale-free or long tails scaling. And once we report the exponents across the three distinct types of interactions, we see that we have different exponents. So this is very interesting because the heterogeneity of interactions changes depending on the behavior or the type of social interaction. So you cannot even aggregate with respect to different social interactions. So essentially the take-home message here is you don't need to aggregate because you can lose important information. So you may ask why this is so interesting, and you will see later why this is so interesting when I will discuss about the applications to the COVID-19 cases. And I also like to to point your attention to the fact that in networks, so the networks have this special feature where small actions, so at the very microscopic level, can have large unintended consequence at the macroscopic level. And this is a feature typical of complex systems in general, and networks it seems to be designed to amplify this type of processes. One example is, for instance, the first tweet of the appearing years ago about this Occupy Wall Street. In a few days, it jumped around the network until it was retweeted by a famous guy, and in just a few months, so it was July and this is September, it led to a protest in the physical world with a coordinated behavior in the physical world. And similarly, a similar thing happened for instance, for the Arab Spring, where from a single tweet you see that it was able to ignite protest overall in northern part of Africa. And here you see the tweet. So this was December. In March, they were already admitting that we use Facebook to schedule the protest and Twitter to coordinate, because Twitter is very fast for spreading information, and YouTube to tell to the world. So this is, I think it's fantastic, because beside the fact that you can really make a change, you can make the difference using social media, using in the right way. This was one of the first events, remind that social media are relatively young, and this was one of the first events where we could collect data at a large scale, and then we can use that data to say something about how coordinated behavior works, for instance. And one of the latest examples, this is the very first tweet in Swedish by Greta Thunberg. You see over here, in less than 1 year, she was able to reach and to coordinate the activities of about, if I remember, 4 million people around the world in more than 170 countries. So this is fantastic. This is the power of social media. And of course, also it's important also to say, to denounce, to say something about bad things happening, like, for instance, the killing by a policeman of George Floyd. So this is one of the first tweets appeared on Twitter about that. There was no George Floyd, as you see over here, but eventually this also has led very, very quickly to another protest, another movement, that is the Black Lives Matter movement. And we have many examples of coordinated behavior, for instance, trying to troll the Trump speech during a rally, and so on. So remind that information exchange plus coordinated behavior is able to ignite a domino effect. This is very important. But as there is a good side of social media, there are also dark sides. And for instance, social media can be used, unfortunately, also to monitor and track individuals, and sometimes also to alter our perception of reality. This is one example happening during the protest in Hong Kong, where the media were reporting that there were accounts deliberately attempting to sow the political discord in Hong Kong, like saying undermining the legitimacy of the protest happening in that moment. Another example is the scandal behind the arresting of 50 million Facebook profiles due to Cambridge Analytica, for instance. And of course, also the bad usage of a central position like the one of a president, where he was using Twitter, for instance, to coordinate very fastly with, potentially harmful behavior across USA. So one question can be, how can we influence information? And there is a lot of work about this also from colleagues. So this image is from one of the works of Phil Mengzer and his lab. And as you can see here, each dot is an account, a social media account, and you have different memes competing. So the colors here are the memes competing for attention. And of course, if there are many of them, there is a kind of information overload. And when there is information overload, unfortunately, it can be shown that the quality of the shared information is pretty low. So the higher the information low, the lower the quality of the information. And something similar happens also when you have this interplay between humans and machines. In this case, the machines are social bots, and that are semi or fully automated accounts working on social media, especially on Twitter, and here are depicted in yellow. And when it can be demonstrated again that when there is low infiltration of bots in a social network, the quality of information shared is pretty high. But instead, when the bots start to be part of the global or the public discussion, the overall quality of the sharing information is low. And we will see a better example later about that. So how can information, so we've seen how we can influence information, but how the information now can influence the human behavior. And here there is an example from a recent paper from my lab, in collaboration also with Emilio Ferrara, another leading expert in this field. And this is the data collected during the Catalan referendum, was a famous referendum in 2017, where they voted for the independence. And there were a lot of problems with police in the overall Catalonia about this event. And essentially here, each dot is an account. The blue dots are humans. The red dots are bots. So semi-automated or fully automated machines. And in this visualization is nice because let's see that the bots tend to interact a lot with the core of human accounts over there. And as we have shown in this paper, here we have the disentanglement of the same information. The bots tend to interact mostly with the influencer, let's say, the most central individuals in the human network. Here the centralities are calculated according to PageRank to account for the directionality. And here you have the attacks they do on group 1, and here the attacks they do on group 2. Group 1 and group 2 of humans interact with each other. We discovered later that one is the independentist and the other one is the unionist. And as you can see, instead, the bots don't interact with each other group. They interact just with the humans. And this is a bow tie diagram summarizing this result. And what is interesting beside this structure of the communication is the quality of the communication. We have performed an emotional analysis, and we have seen that this group of bots was fueling this group of humans with negative information, with negative emotional information. The opposite was done by this group, where positive information was fueled. And if you can imagine that these two groups are already opposite by the type of political ideology, and more they are fueled with negative and positive content. So in practice, these bots are sustaining the conflict. That's why it's important to understand how they work. And how we did that. So without going into details, we use a topological analysis, so network science, essentially to reveal the two groups. And we have used some machine learning to identify both and humans, and computational linguistics analysis, again, to identify which one of the two was the independentist, the group of independentists. Then in a successive work, we have discovered other interesting things. This is during the Italian elections, for instance, again on Twitter. And here the colors are mapped to communities. And those communities we have shown that identify pretty well political parties and press. So it's not just a community detection algorithm of the top of the network. This is the social bulk. So it's a way to filter the network according to the distinct type of interaction. We use a kind of multi-layer structure of this network in order to find these individuals. But interestingly, there is this dot here with at the center there is a human account, and around that there are 2,000 social bots. So that guy was using those social bots to gain status, to gain visibility. And we have performed analysis about this behavior, making a distinction between bot and humans. And again, here you see, for instance, that they generate both cascades as information cascade, as I explained at the beginning, but the distribution of the sides of these cascades are different, with some overlap, but they are different between bots and humans. And then you can use the cascade rate and the number of followers to try to understand, for instance, the accounts acting as influentials, as of broadcasters, or hidden influentials. In that case, for instance, here you see this dot over here is an hidden influential because that guy was using tons of bots to generate a lot of cascades, but having a very small number of followers compared to other people in the network. So let's move quickly to another application about the social burst. So as I was saying at the beginning, you don't have to aggregate all of the information because it's a reach of patterns over there. And this is just a correlation analysis of the number of tweets of the volumes that you have, like this over here, of tweets versus retweets, tweets versus replies, and retweets versus replies. And you see the different correlation patterns emerge over time in the case of the discovery of the gravitational waves. Then you can change event. Think about the Boston bombing of a few years ago. And again, you have correlated patterns, but with distinct depending on the type of interactions that you consider here. And again, another type of event is, for instance, the final of the UEFA Champions League in 2016. So the message here is that it's very rich of patterns, and we want to understand those patterns. So we focused, instead of focusing on the how of the rise of collective attention like this, we tried to focus on the spikes on the top of this collective attention, spikes over like this one. And in this case, you have a spike that is a very abrupt, so an instantaneous burst of activity or triggering a lot of volume. In other case, you have at the same time scale, be aware, you have instead an abrupt rise, burst over here, but with a slower decay. So what is the difference in the two cases? And we have discovered by analyzing, this is all real data, that you have the coexistence of a rich spectrum of correlations, connecting bursting retweets with replies and so on. There are some models, or there were some models in the literature trying to explain the type of burst and of activity, and they were doing a very good job, for instance, in describing also the emergence of power law behavior. But unfortunately, those methods were not able to provide a clear understanding of the fundamental mechanisms behind those spikes. And as a physicist, I love to learn the mechanisms behind. So let's think about our model and an example, a practical example. So this is again Greta Thunberg, genetic user, and she has a lot of potential receivers that are her followers, and we indicate with KI. At some point, she decides to post a message. We call this message I over here. And of course, this message will have ki potential receivers. Not all of these receivers will see that message, at least on a short time scale. So some of them will receive this, and we indicate this with the probability, with this probability over here. And even if they read the post by Greta, it's not granted that they will react to that post. So we decide to put another indicator here, another parameter, where encoding the fact that there is a certain probability of reaction to a given message I. So this probability is related to cognitive effects, the probability of a reaction, of getting engaged. And this number instead is related to topological effects. So you see here that we are trying to account for both the topological effects and human behavior. And how we do that? So if you think about the number of responses, so of engaged users will retweet and reply, for instance, to that message at a given time t, we can make this ansatz, so this assumption that is distributed as a binomial distribution, depending on the overall number, the effective number of users, that is ki times the probability of activation, and the probability, or the probability of, yes, of activation, and the probability of reaction. Why I say that? Because there is real data supporting, yeah, here it is, there is real data supporting the fact that a binomial distribution is a pretty good approximation for doing this. So imagine to have more than one message, so in principle n messages within a time window t. So the expected number of social bursts to that message, to a single message, let's say, will be given by this relation. It's very, very simple statistics, it's binomial statistics. Then the overall number of social responses to all messages will be just the sum of all of these numbers. Then this sum will just be mapped to this other sum. So the collective behavior at time t in our very simple model will have a piece connected to topological effects, the k, so let's say the number of followers of the user, and the cognitive effects, the probability of activating about a specific message. How can we exploit this? Well, we can make simple assumptions about the degree distribution, for instance, and about the probability of attention, this probability parameter of getting some attention about a message. In this example, we call homogeneous, we say that the degree distribution is homogeneous, or distributed like a Poisson. And instead, the probability of reacting is constant across all messages, not in time, but across all messages. This for us is democratic attention, because essentially you retweet with anything that you interact with, essentially. Then there is the heterogeneous assumption, where you have still the democratic attention, but the degree distribution is like a power law. And in the case of Twitter, from the real data, one can fit that this number over here is 1.2. So the overall exponent will be minus 2.2. And then there will be the mix of these two, of this effect, and what we call preferential attention. That is, now the attention is no more proportional, it's no more constant with respect to the message, but it's proportional to the number of followers of the individual who posted that message. So it's another way to say mathematically that if a message comes from one that is perceived as an influencer, it will get more attention. Okay. Then, and I will not go into all the details, but this is just the general idea of thinking about this problem. We can map this model into the sum of fat tails variables. And there is a whole theory about that. Without going into the details, the interesting thing is that you can analyze the fluctuations of these bursts, like seeing, so looking at the number of the size of the burst minus the expected value. So here you have the square of the variance essentially divided by the expected value of the size of the burst. So this is a way to quantify fluctuations, for instance. In the homogeneous case, you can see that the size of fluctuations goes to 0 for the increasing size of the system, In the heterogeneous case, this is also happening, except for this case where you have a specific case. So where mu, this parameter over here going the exponent, is between 0 and 1. So this is interesting because it means that fluctuations can be arbitrarily large. And once you go to the preferential attention, you can map everything to this same case just by seeing that 1 plus mu is mapped into this other exponent in this way. So what happens here, that democratic attention is going to be with a model with alpha equal to 0, and you will have mu equal to 1.2. And when you have biased attention, so you are more likely to be interested in what an influencer is telling you, you have alpha equal to 1, for instance, and mu is smaller than 1. And when mu is smaller than 1, here there is a big difference. Because when mu is in between 1 and 2, the fluctuations will go to 0. But when mu is between 0 and 1, fluctuation can be arbitrarily large. And this is exactly what we see in the data. So what we have done was to slice our time series for the volume and to essentially build a measure of spikiness. This is just the maximum that you have across the windows, so within a window, sorry, divided by the average value that you observe in that window. So it's, this measure is suitable for doing this type of analysis because it accounts for large deviation, and its scaling overall can be calculated analytically. So as I said before, the nice thing of this measure is that we get rid of this parameter, the activation parameter. So this is no more relevant. What is the probability of reaching in your followers? And this is interesting. Then we use the value of mu got from real data, from measured independently, not from us, that is 1.2. Then we have just two hypotheses where we vary the value of the exponent alpha. So essentially, this is a almost parameter-free model because we have two hypotheses corresponding to different values of alpha. And once we compare with the data, these are the interesting results. So the colored areas here are related to the three models that I have discussed. So the homogeneous, the heterogeneous model, and the heterogeneous with attention, so the preferential attention model. And the dots over there are points from real data, okay? So from the time series of volumes that we have observed. And we show here 4 different events, from the election of Pope Francis to the Festival of Cannes, the discovery of gravitational waves, and the A finals. So very different events. And the agreement between the model and the data is when you have the dots inside the shaded area. So essentially, you see here that this is interesting, that the social burst that we're trying to measure in replies, because these panels are related to replies, fall within 2 models, essentially. The one with the heterogeneous model and the one with the preferential attention when the number of tweets is very large, when the number of messages is extremely large, I would say, and the rate of information is huge. When the rate of information is huge, we go back to what I was saying at the beginning, that there is information overload. So what we have discovered from this analysis is that when the activity is frenetic, so more than 50 posts per minute about a topic, social endorsements behave in different ways. So if the activity is frenetic, then homogeneous interaction, democratic attentions apply to retweets, for instance. And if the activity is not frenetic, we have still democratic attention, but the effect of heterogeneous interactions are relevant. The things are more complex when you have social responses like mentions or replies. In replies, for instance, we have discovered that the preferential attention is playing an important role to explain the size and the statistics of the burst of attention. So you can understand now that the burst of attentions can be very relevant when you have a global public health crisis like the one that we are living right now during the COVID-19, because it's a way to drive the collective attention of users. And in order to better understand some of the things that I'm going to say in a while, it's good to understand this type of models. So imagine that there is a number of users, here the nodes, but that they can interact with according to different types of interactions. So I have family interactions, and I can have also business interactions with the same people. Imagine when we work in the same place with one of my relatives, for instance. And the same applies, this is for the physical world. The same applies for the virtual world. So in the online social networks, I can have friends both in Twitter and Facebook, or in Facebook or not. So overall, there will be different connectivity patterns between the two distinct social media, as well as there will be overall distinct patterns here. Why this is important? Because in this physical layer, there will be the spreading of diseases and behaviors. And in the digital world, instead, there will be the spread of information. And at that time, so when I started to work on this, my intuition was that these two processes are really entangled in some way. But during the COVID-19, we have discovered that this is actually true, and we have quantified this entanglement. So let me spend a few words about multi-layer networks, because I have been working on it from a theoretical perspective, also from application for a while, as Michele was saying at the very beginning. And what is a multi-layer network? Essentially, is what I was saying before. It's a collection of networks where each type of interactions is encoded into a distinct layer. So each layer here is a network, and the nodes of these networks are the same. So there are some nodes not existing in all layers, of course, but there can be nodes existing in all layers. And there is an interlayer connectivity like this, or intralayer connectivity like the dashed lines over here, connecting and practically coupling the layers. And a physical node is the collection of all the same nodes and its replicas across the network. Instead, we have the replicas or state nodes, the nodes, the physical node considered just in one layer. Then we have very different models depending on the data that you have at hand. If you have no information about interlayer connectivity, we talk about edge-colored multigraphs. If you have instead connectivity information, we talk about interconnected multiplexes, or interdependent networks, or general interconnected networks. But everything depends on the data. And why this? I said this also before. Why this is interesting? Because the fact of having coupling different layers has a deep impact on the dynamics and the emergent dynamics related to driving collective behavior. So the general idea behind the mathematical formulation is that you assign a canonical vector in a Euclidean space to each node as this, and then you build the adjacency matrix as a combination, a linear combination of canonical matrices, and also, of course, of Kronecker products of canonical vectors. And then we just use another, this other representation that is in terms of covariant. So it's another notation, but essentially the idea is this one. Where here you have a vector that is a symbol with one index, and a matrix that is a symbol with two indices, because they encode interactions. And then we use a tensor like this to encode each layer here. So this layer is encoded by this tensor, this layer by this tensor, and so on. And of course, also the interlayer interactions are encoded by tensor like this, because I need a way to say how the nodes in this layer are connected to the nodes in this layer. So I have one connectivity matrix, or a tensor, adjacency tensor, for each pair of layers over here. And then we found an interesting way to put all of this information together in this way. So without going into the details, you have this object right now. It is the multi-layer adjacency tensor, and it has 4 indices. Why 4? Because with 4, you need at least 4 numbers to indicate which node in which layer, and we are at 2, is connected to which other node in which other layer, and we have other 2. So in this way, with 4 coordinates, it's roughly speaking, it's enough to identify a relationship in a multi-layer network. And this is more or less the increasing in complexity, that you have. A node is, in terms of tensor, is a scalar, essentially. Sorry, it's represented by a vector. A complex network is represented by a matrix, a rank 2 tensor, and edge colored by an hypermatrix or rank 3 tensor, and a general interconnected network, a multi-layer network, by a rank 4 hypermatrix, if you want. So it's a more complex object. Then, of course, you might say, yeah, but you have to work with tensors. Yes, but it's not that complicated at the very end. We have proposed a way to map information in some way according to another method proposed by called in 2009. This is called matricization of flattening. It's a way to change the dimension of an algebraic object without losing information, so while preserving information. Here you have a matrix that is changed into a vector, and from the colors you see that the information is preserved. So this, you might say this is a trick, and in fact it is. But this trick can be used to map this complicated object, a tensor with 4 indices, into a tensor with 2 indices, so into a matrix, what we call a Supragensy matrix. And here you see that each layer is mapped into a block matrix within the diagonal entries of this supraadjacency. Instead, the off-diagonal blocks encode the interactions between the layers. Yeah, here is the slide about that. So in the block diagonal, we have the layers, the connectivity of the layers, and the off-diagonal, we have the connectivity between the layers. So with this just with recipe, the overall flow, working flow, is to start from raw data, where you map time series or higher order information into a multi-layer network model. Then the real model requires a multi-layer Genesis tensor, which is complicated, but you can use a flattened representation for practical purposes. So here, what's important is to remind that this type of modeling is important when there is a trade-off between intralayer and interlayer links. And you have to use, so you don't have to use multi-layer analysis when this coupling is very weak. So essentially, individuals in one layer do not alter the behavior of individuals in another layer. But when this is the case, instead, you need to use a multi-layer model, because otherwise you can miss very important relevant information. Then there is also the dynamics on the top of these networks. Here, just to give you an example, this can be the dynamics of the spreading of a rumor on the top of multi-layer network. On here, there can be the spreading on 2 different and competing dynamics identified by 2 different colors on the same network. In this case, we talk about coupled dynamics instead of single dynamics. And again, we have a mathematically consistent way to indicate all of this, but I will not go into the details. But why it's important to know its existence? Because depending on the way you couple 2 layers in a multi-layer network, a message, or generally information, can diffuse faster or slower. And this is very relevant for practical applications, because since our world seems to be really well modeled by a multi-layer network, in some cases it's more clear now why information spreads so fast with respect to single layer in isolation. Then you can use the dynamics to do a lot of other things, like, for instance, finding communities within these networks. You can try to reduce the complexity of this network either structurally or functionally. So it's rich of applications, but I have no time really to go into all the details, but I will be happy to answer your question or your email if you have any about that. So let's move for the second part and last part of the talk to applications to COVID-19. So this doesn't need many introduction. This is the number of COVID deaths over time from March 2020 around the world, and you see that there is a rise overall across any country. And what happened is that from a complex system perspective is that you have a shock, essentially, like the COVID-19, investing our complex society, that is a system made of many subsystems, like the economic one, social one, and so on. And this shock propagates, and with its time and different amount of time reaches different subsystems, leading to failures and systemic failures then. But of course, as in any complex system, there will be a time at which the recovery will start to appear. And you can, if you map this concept into some mathematics, so in terms of functioning of a system, in this case of society, you will see that was the starting point, the baseline. Then you have the shock, the pandemic shock, and of course you have problems. And then society start to work less better than before. We have public health problems, financial problems, political problems, but also social problems, as you see, you have protests and so on. This is all expected. At some point, you achieve the lowest resilience possible. But after that, you start to go back to the baseline in possibly different ways. I don't want to spend too much on this, but how you can do that? With innovation, for instance, or with adaptation. Smart mobility, smart working, for instance, or a faster transition to digital technology will help all of us to do this. You are experiencing actually exactly one of these, because we are doing a digital, we are exploiting digital technology to do this school. In another universe, we will be all in Turkey doing this in presence. So essentially, the fact that we have a virus starting from China or from anywhere else in the world, but for COVID-19 it's China, it led to a pandemic, of course, due to human mobility and social contacts. Then, of course, we need to respond. So the propagation of this shock requires us to make lockdowns, for instance, and lockdowns generate problems to stock markets because the economy is stopped. But on the other side, you have also other stuff going on. You have the emergence of infodemic, so this problem of the disinformation competing with reliable information, and people is getting disoriented by all of this information, and once they believe into the bad one, there can be problem in the physical world again, because for instance, this is the case of people burning 5G antennas. If I remember correctly, this image is from UK. And to some extent, we live in the disinformation era, and we have to coexist with that. We have to embrace the uncertainty related to information. We have to understand the processes behind how disinformation spreads and, let's say, compete with the spreading of information. There are many papers, not related only to COVID-19, papers from colleagues, but also from our lab, related to this fact. For the case of COVID-19, let's say that this was expected. The WHO in February 2020 warned the governments about the possible rise of this infodemic. That is an overabundance of information that can be accurate or not, that make hard for people to find sources which are trustworthy and where they can find reliable guidance to take decisions. Those decisions can be to wear a mask, or in the case of vaccination, to get a jab. And this is a very nice visualization from the Poynter Institute, where each dot here is a piece of debunked misinformation or disinformation. And the colors and the groups here encode the different types of topics. So here there is disinformation about the spread of the virus. There are different disinformation about the lockdown, the signs, symptoms, and so on. And how this information spread? Well, we are still investigating that, but it seems, and now that there are many evidence now that influential people again is getting a crucial role in this. Here we have the case of a piece of misinformation about the fact that COVID was not a deadly disease. And this piece of information was retweeted and was shared by an influential individual in US. And his network actually very quickly replied and responded to that. And very, very quickly, the thing arrived to to become a political fact, and started to be circulating within the political subgroups, and so on. And this is concerning because from a very recent analysis published by the Reuters Institute for the Study of Journalism at the University of Oxford, it seems that almost 60% of the misinformation, disinformation is reconfigured. So essentially, people are taking really reliable information and they are changing things to alter the reality. And less than 40% are really fabricated by scratch. So the most of the misinformation circulating sounds like technologically simple, like technologically possible. And there is also a very important difference between top-down and bottom-up misinformation. Here you have for instance, that 20% of the total sample of misinformation shared in social media comes sorry, the 20% of the total sample of traditional media content is responsible, is shared by 69% of, attract more than 69% of engagement. So this is very, very relevant. It means that we are facing a kind of super spreading events like the ones observed during an epidemics. And here there is another statistics which is very concerning. We have here 3 different platforms, Twitter, YouTube, and Facebook, and this is the percentage of posts which are rated as false, but without a clear warning for the users about the fact that it's a false content. In Twitter, this is up to 60%, while in YouTube and Facebook is between 25 and 30%. So let's go to our modeling scheme, where we have, on the one end, we have the epidemics, where the virus travels through the transportation network with the speed of the transportation network, so with the human movements. And of course, once arrived into a geographic area with the time scale of the social contacts. And here, instead, we have information traveling through social media and phones. So you have here the infodemic process with traveling at a faster speed because, of course, information travels faster on social media through the internet. And our hypothesis was that these 2 processes were actually entangled. So you can understand one better if you take into account also the presence of the other one. And how we do that? Essentially with the same models explained probably by my colleagues in the previous lectures. And here, just give a hint. Here you have the macro scale. Each dot here, each point is representing a population, so a group, a community, if you want, and that is representing a kind of mesoscale. But within the mesoscale, we have then microscopic interactions, so the microscale, where we apply the laws of complex contagion that, as I was saying at the very beginning, leads to information cascades and also in the case of epidemics, for instance, to super spreading events. In the case of infodemic, and there is a lot of confusion about the infodemic, so let me spend a few words. Infodemic is not a synonym of fake news and that's it. So it's not the amount of fake news, it's not the amount of posts, because that's related to volumes of things, or human activity. It's not just related to the volume of human activity, but it's related also to the way the human activity reacts and responds to the contents circulating online. So, as I was explaining at the beginning of the second part, this guy over here, this guy over here is exposed, that is the right term, to this information coming from this guy, for saying that the government patented a vaccine for the COVID-19 years ago. but is also exposed to reliable news spreaders, like saying policies like following social physical distancing, wearing masks, and so on. Then this guy has a dilemma, because has to understand which other guy has to be taken into consideration. And then he or she is confused, because most of the time the number of users supporting one type of reliable information is comparable with the number of users supporting unreliable information, or the relative weight, so the perceived importance. Remind the model about the preferential attention we discussed before. If this guy has a lot, so is a Trump, just to make an example, of course, it will have a lot of weight when spreading information. So this generates confusion, and this is the dynamic of confusion that is related to the infodemics. And this is just another way to show this. You have a network over there where you have the green areas are where the users are talking about reliable information, and then there will be unreliable information overlapping and competing for attention. And you will have overlapping users and communities where you have both of types of information circulating. So we have developed a mathematical approach to understand better this phenomenon. I will go into some detail later. But the important thing here is that we have developed a quantitative way to analyze this phenomenon, and this is called the COVID-19 Infodemic Observatory. You can play online with this interactively. You will have a lot of information of indices over time. It's updated daily. And you have also other, you can perform a lot of analysis, a lot of comparison across countries, across WHO areas, and so on. And up to date, we have performed, so this number is not updated, but up to a couple of days ago, this number was 2.5 billion of tweets analyzed, with more than 150 news analyzed around the world. And yeah, I have updated these numbers with the latest one. So as I was saying, we have many different indicators over here, and sorry, it doesn't work. It doesn't work anymore. Sorry. Well, I don't know why. It doesn't matter. So here we show some of these indicators and its evolution over time. And together with that, we have worked with the WHO to develop also policy recommendations about the areas and the regions of low, medium, high, and high infodemic risk. And together with, so here you see, for instance, an example of what I was talking about in terms of policy recommendation, and also of the type of information circulating. We have 7 distinct types of information that we label, from science and mainstream media to clickbait, politically oriented information, fake news, and conspiracy theory. So more or less, the observatory works this way. We extract metadata from Twitter. We perform a lot of analysis, distinct levels of analysis, using machine learning in some cases, for instance, for performing both human detections or psycholinguistics. We use also for geocoding. But we also use human coding for checking sources of like the URLs and the domains used to spread a specific type of information, for instance, from blogs or from mainstream media. And we have also used network theory to understand information cascade and use this understanding to develop risk indices. Here there are some statistics, but we can skip that. And eventually, we performed a risk analysis where we have defined the infodemic risk index in terms of the exposure that users have to unreliable information with respect to the overall exposure to both reliable and unreliable information. This is pretty similar in spirit to the epidemic attack ratio used in epidemiology. And you can calculate this number, this index, using either the structural information that you have about the network, or using, for instance, the type of interactions between the users. In this case, the interactions are retweets, replies, and so on. Once you do that, you see in this plot that you have very interesting correlation between the two measures, of course, but there are also deviations. So it's interesting to use the two measures separately. And of course, the structure behind the network structure behind for instance, bots and humans, verified user and unverified user are different. There are some topological differences that we have discovered. And we have also discovered this very interesting behavior. That is, I am sorry that it doesn't work anymore, the pointer, but essentially we have discovered the fact that we have an infodemic wave hitting countries with some relevance, with some intensity, but once you have the epidemic wave hitting the same country, the epidemic wave starts to decrease. So there is a kind of feedback between the two waves. This was very striking in the case of Italy. You see here that there is a striking difference between the end of the infodemic wave, at least the drop in the infodemic wave, and the rise of the epidemic wave. But this is something that we have observed also in other countries around the world. We have performed statistical analysis, of course, and we can say safely that once the epidemics start to become more important, more relevant in a country, the infodemic about the disease start to decrease. So this tells you nothing about other problems like vaccine hesitancy, stuff like that. This is only about the exposure to unreliable information quantified in terms of the infodemic risk index. And of course, this we have collaborated with WHO, as I was mentioning before, and we have presented this into several infodemiology conferences, and we are now in touch with several organizations in order to allow them to better understand and exploit practically this point. And in this resolution of the World Health Organization in May 2020, they have put the infodemic as a real problem, and in the real world with recommendations or the first recommendations for governments. And with this, we are going to conclude. This is another very recent work. It's still so it's going to appear in the next days into Social Science and Medicine journal. And here you have a kind of this is a map of the interactions we observed in Twitter about COVID-19 between the distinct users, different users, and the clusters encode with the colors tightly interacting users. And we performed human coding. Again, we have identified, for instance, countries in this map, in this cosmic web of Twitter interactions about COVID-19, but also ideological groups, like, for instance, the US Republicans. Then we have tried to understand also the content, or say to better characterize these groups in terms of institutions, human bots, news media, etc. And also of political leaning and the type of the news consumption within each group. And we have discovered a lot of very interesting patterns, like, for instance, the group of the US right wing, that is, yeah, it's probably over there, that is also polluted by a lot of disinformation, reliable information in the same group, as well as, for instance, the clickbait was the most relevant type of news consumption within the group of K-pop fans, etc. Then we performed also a lot of network analysis to understand if the structure within the groups was random, and is not random at all. There are some very interesting patterns. I hope to have questions about that. The message here important is that those structures are relevant because they centralize information. So within the groups, what we have discovered is that there are a few individuals accounting for the majority of social actions and of news shared within that group. Like saying that social media actually, or at least Twitter during the COVID-19, was not really that democratic arena that you can imagine, but it is instead highly centralized around a few individuals. And this, of course, it's pretty relevant when you go to analyze also the type of information that is spread and shared by those individuals. So, and to conclude, we have a lot of limitations as well that we have to take into account into these studies. For instance, the bias, the sampling bias of the data. The Twitter population is not representative of the world population. We know, for instance, there is an unbalance between male and females. So there is an unbalance between people with a degree and not, and so on. There can be both hijacking or changes due to policy platforms. One big change in Twitter was the massive verification of users, for instance. There can be limitation in the API, so you cannot collect all the data in some cases, or there could be a shift towards sources that you are not able to track because they are too new, and you have still to discover those sources. Then there could be, of course, issues with geocoding and poor model calibration. So all problems related, for instance, to your to the training of your machine learning models and so on. So my message is not to think about using, for instance, artificial intelligence to fight this information, but to use it to assist humans to fight this information. And here is just a summary of what we have seen today. The importance and the relevance of information cascades and overload, the altered perception, social manipulation due to both pollution and coordinated behavior, as well as spreading patterns which are not trivial due to information content and network structure, and the fact that we need big data analytics, but knowing the limitations in order to fight this information. So thank you very much for the attention, and I'm here for your questions.
Thank you very much, Manlio. Thanks for a great lecture, very dense of concepts. Okay, we have room for questions, and the first one comes from the chat, actually, from Hadi. I think there are 4 questions already, but that's great. So, what method exactly do you use? I don't know if you can read the chat, but I can also read the questions.
Let me stop the sharing. Yeah, I can see the chat. So thank you for your great talk. Here's some question. What method exactly do you use to detect bots? Well, we use different methods. We have we perform a kind of ensemble learning where we have trained models using random forest, but also deep learning architectures, and all the details are in our papers. Let's say that we use some information that we gather from tweets in real time. There are 10 features like their number of followers, the number of people they follow, and other information that we can extract from the data. And then we have trained our models on thousands of manually labeled data, so users. So we use essentially that. In your article, you and your colleagues introduce 9 categories of external link sources. I am interested to know that where do you put sources like Wikipedia and small, local, non-famous, non-political, non-fake news agencies? Well, the details are again in our Nature Human Behavior paper, where we list all the sources that we use. So from journalists and also academic sources, where that we use to gather together our internal database. And but Wikipedia, for instance, is inside, if I remember correctly, other, the category other, because We know that there are reliable information we give, but also unreliable information. So like in the case of YouTube, we cannot perform an analysis of the content of YouTube video. So also YouTube in this case is classified as other. Instead, we only use sources where we are sure about the classification. Like the BBC, for instance, is classified as mainstream media, while Zero Edge is fake news, if I remember correctly. So then when the measuring traffic manipulation on Twitter, also mentioned cyborgs in addition to people and bots, partially automated accounts which show some human behavioral patterns, but post with machine-like frequency. Do you think considering this type of users in analysis like the one you introduce in this talk can result in better models? Well, I think this is relevant. I have shown actually one of the one application about that when I was discussing about the augmented humans during the Italian elections analysis. So they are called also cyborgs. And yeah, I agree that they have a role. They can have a role because they have the computational power for performing social manipulation of machines, but they are literally driven by humans. So they are not automated. So they can play a role. So I agree that accounting for them in models might be interesting. Then what tools do you use to visualize networks except for Jeffy? Well, I use R, and all of my visualization are literally done with R. In some cases, it's just using iGraph. In other cases, it's using a lot of convolution of codes to maximize the information that.
So this is interesting to me, Manlio. So you're using R and not Python, or using both, like Python for other
Oh,
stuff?
no. I use mostly Python for doing some analysis. So all the big data stuff, collecting data, is done with Python, but the visualization,
okay,
yeah, is done with R because there I have full control about the low-level details. So, for instance, there is the beautiful image about the attacks by bots on humans during the Catalan referendum. That was done by scratch using R. I don't even use iGraph for that.
Cool.
So then there are other questions.
Yeah, there are other questions in the chat. What is your opinion about using click or motifs in predicting bars of events causing collective behavior? Have you used this approach in your research?
Well, it's a good point, but using clicks and motifs requires also the knowledge of the underlying network. So in our analysis, we have seen we're able to analyze the rise of collective attention with this burst without by providing a method with not requiring direct knowledge of the underlying network. But of course, I think that using the more information about the underlying network when it's available can increase our our understanding of which topological features can be important. In our model, we have demonstrated that having a huge degree, so that the degree distribution in general without peculiar topological patterns is pretty relevant for the social burst.
And then a question about, are tweets with no geolocation discarded or inferred? I mean, so when you infer the location of the tweet, what do you use?
Yeah, we have distinct type of importance that we assign to tweets. When the information is inside the tweet in terms of coordinates, we call them golden tweets because, of course, the information is to the best of our what we can gather is accurate or is considered accurate. When there is no coordinates, we try to infer this information from the user, the location given by the user in the profile, for instance, and then there we perform geocoding. But we give less importance to this type of tweets because, of course, many users provide the correct location, other users provide fake location or the location of multiple locations or just fantasy information. All the tweets without this type of information are just discarded. So we are not used to say something about the country.
Okay, other question from Rui. In your opinion, what makes a tweet become a super spreader?
Sorry, can you repeat it again?
What makes a tweet or user, actually more a user, I would say, become a super spreader? What are the features? And
yeah, so this is Michele, you are working on this as well. So it's probably a $1 billion question, because knowing the exact answer to this question will allow companies to make a lot of money on social media. So, but it's a very good question. I have no ultimate answer to that, but I can tell you that there are a lot of factors. Of course, the number of followers plays a role. The fact that you are an influential individual, like a politician or a celebrity, of course, has a lot of impact. But also the position that you have in the network is relevant. You might have a smaller number of followers, but living in the middle between distinct communities. So having a high betweenness, I will say. And then your messages will quickly percolate through different communities at the same time, and your message will be spread equally faster. So there are a lot of factors, in my opinion, that are both topological, but also in terms of content that are relevant. In terms of content, but I am not a psychologist, so I don't want to say a lot about that. But if you spread a piece of information that is negative, or that is known to be very emotional, it's very likely that you will trigger the attention of people, just because, as Kahneman was saying, we are triggered by bad news, by bad things more than good things.
Can I ask a follow-up question? Because like I asked about this, what makes this a super spreader, for example, for either the user or the tweet. I also wonder the role of luck in this. So for example, you gave an example of like the very first tweet of the Floyd Black Lives Matters. It doesn't seem to come from either a celebrity or something, but just like it doesn't seem to be very different from other similar cases. But this one kind of probably is one of the most frequently tweeted tweet. So I was wondering like how luck plays a role, because in network studies in humans, I'm a psychologist, I'm a social psychologist, and there's some work in terms of how one person becomes a popular in a class, and can be luck can be a big role in this. I was wondering how that is related in, let's say, for example, tweet on online social media network.
Well, it's a very good point, and I agree with you that luck can play a role, but I don't know about studies, quantitative studies, that are able to assess how much luck can play a role. For sure, I think it's not just a matter of luck, because it's an interplay of different factors. The example you were bringing about the Black Lives Matters. In that case, the person who made the tweet was not super central, was not an influential, but she was providing a piece of information that was really important, really concerning. So she was throwing out there in the network, in the public arena, that a policeman killed a black man. So, and this is huge in terms of the emotional reactions that you can get. So I think that it's not only the topology, it's not only the content, and probably what we call luck at the very end can be just a complicated combination of these factors.
Okay, so still question coming. One question, it's the last one, but it's easy to answer, is what is the best package to analyze multi-layer networks, and since Manlio has developed packages,
So
I think.
thank you for this question. I can guarantee that it does not come from one of my students, but as Michele is saying, I have developed across last years a package that is called MuxViz. It's free, it's open source, you can find it online and on GitHub. And let me say that in the next month, there will be also a book about it, explaining how you can use it in practice. So it will be published by Springer, and there will be a good interplay between the theoretical backgrounds and so are you still there?
Yeah, we hear you, but you were just frozen for a little.
Okay, so it seems there is a problem. Okay, but I can continue. So essentially, MuxViz, you will find this on GitHub. Now it's fully in R.
Oops. Okay.